Hey, hello there, and welcome back. Welcome back to Advent of Code Day 21, and this rather hard part 2, I would say. And with rather hard, I mean I have very little idea of how to solve this. So this is a continuation of the previous video. So if you haven't, I guess if you haven't watched that, this won't make any sense. But basically, we did part 1 in a very naive way. Part 1 is about, counting how many steps an elf can make. Not how many steps, sorry, how many places an elf can visit exactly after 64 steps. And it has an interesting parity thing in this and blah blah blah. The way I implemented this was using a Dijkstra algorithm, like a modified Dijkstra thing that lets you iterate over reachable tiles, and it gives you back the cost of this. So basically here I'm calling this Dijkstra reach. Gives me an iterator, and what I do is, this thing for the neighbors is I cut the neighbors function on some threshold. Originally this was 64, but I modified this. You can see it's modified to play around with some numbers and trying to get to part 2, because part 2 extends this and asks us to count the numbers exactly these. To count the tiles after exactly this huge amount of steps, 26 million and something. And this is something that grows kind of quadratically, so the answer of that is going to be something like this number squared. On that, it grows like a squared thing, because this is basically a square that you make, a 45-degree rotated square, like a rhombus or diamond. So that's what we're at, and we had some clues for part 2. We realized that the input, I should make the fonts lower for this. The inputs, not only does it have this interesting diamond shape drawn here, which is already kind of suspicious, let's say, but also the start of both the input and the sample is always in the middle of this square, and it's a square grid. And then, by the way, in part 2, it asks us to do this after this amount of times, and this thing extends, repeats infinitely to every side. So it's an infinite grid. But the thing is, we have checked that moving all the way to the left, I moved the starting position there, but all the way to the left, or all the way to the right, or all the way up, or all the way down, it's all empty tiles. So we don't have to care about walls in there, and that gives me the clue that basically we're going to cover many of these super tiles, of these maps, let's say. I don't know how to call it. A tile is a single one of these, but this is a super tile that repeats. We're gonna cover a lot of them with our 26 million steps, but most of them are just going to be the same. They're exactly the same. How we can, what are the tiles that we can cover, because to all of them we can reach this is 131 by 131, and this is at 65 or 66 if you want to use one-based indexing, but I'll use 65. That means that if you move 65 to the left, or 65 to the right, or 65 up, or 65 down, you can always start at this place. This is the, on the next repetition, the minimum distance to reach to any tile. By the way, the borders of this are also all cleared of walls. So all the borders, one tile border of this, is also cleared of walls. So you can move basically to any neighboring super tile by like the minimum distance of just walking straight up. You don't have to avoid any walls. And so like the pathfinding would be the same on every tile. Every tile that is exactly to the right or is will be repeated. The ones that are exactly to the left will be repeated. The ones that are exactly up or exactly down will also be repeated themselves. Not like they will be the same for the right ones or the left ones, although I suspect that they probably will, but that doesn't matter. Like all the right ones will be repeated, all the top ones will be repeated, and so on. And also all the diagonals, because you can reach the diagonal. This would be like 65 plus 65, you would be here. So if you want 1 and 1, you would be like on the next diagonal one. And that's, you know, that's the minimum distance also to get to that. You can get in a straight line. And straight, I mean straight down and straight left to get there. And that will be the same for all of the tiles. So if you imagine this is a giant rhombus, you can divide all the super tiles in like a couple of categories, all the things that are up, down, left or right, and in the diagonals. And those things, yeah, should be repeated basically, and should be all filled the same way. So I guess we should be able to find some way of like counting them directly and like doing some arithmetic to get to the actual solution. So that's kind of the first insight. And the other insight that we had was that these numbers still have everything open like before. This is the number of steps that we need to make, and if we do a mod of this and 131, it gives us back 65, which is exactly like where we are standing, like how much we need to move to get to the side, which I think is no coincidence. So it means that, well, this minus 65 is a multiple of 131. Exactly what does that mean? I'm not exactly sure, but I'm sure it's not a coincidence. We can think about that maybe, but the way I'm thinking about this, that you can reach all the tiles to the sides exactly in 65 steps, and then you can sort of like repeat, repeat like the reach for that tile, like they will be the same. That's kind of my idea. Still not really a clear idea, but yeah. And also if we divide this number, like this number minus 65, and we divide it by 131, so like how many super tiles, like, or entire super tiles, something like this, we would be covering to each side is like 202,000, which is a biggish number, but not so much. Like if we need to do something linear to cover this, we should be fine. But I think we might even get like an actual expression to do this. So okay, that's kind of the insights that I have. I want to like try something out for this, but I'm not sure how to get the answer. But I don't want to like get super stuck on this part 2, because maybe this is like a super hard puzzle for this year, kind of like last year's unfolded cube thing that was so difficult to solve. So I want to give this thing a try, maybe an hour at max, and see if we can come up with something. So one thing that I was analyzing the other day was like a super minimal example of 3x3, and trying to think about this. I think I want to expand this little example a little bit. So I will use a 5x5 super tile, and probably I want to turn off the ligatures for this because they are annoying. But let's say I want to try maybe a 5x5 to have the ligatures here are screwing me over. Ligatures. There should be a UI setting for this, but anyway. So in here, I'm recreating like kind of like a minimum example of having some walls, but also having everything to the north, south, east, and west, west and east of the start cleared, and also the borders are clear. But walls exist. That's something that we cannot just assume. If walls didn't exist, this would be kind of a much more trivial thing. Yeah, I think it's we could get like a quadratic expression to calculate this in a very simple way, I think. So I want to have like 5 of this repeated to try to find the actual, I don't know, to have something that repeats indefinitely, kind of a bit larger than what we have. Oops. Let's copy this, let's paste, and well, yeah, let's paste a couple. And let's already have the 5, and here I will just, oh, we also have S in here. Well, let's replace all the S by a, sorry, that was dumb. Did I copy this thing? 1, 2, 3, 4, 5, 6. Oh, it's 6 copies. This is 5. Okay. Okay. Should be dots. Dots here. That was very good editing. Okay, so here we have like a minimal but not so minimal example of starting with this thing. So the size of each tile, let's call this thing super. I will call this super tile, like not each tile, but in this case the 5 by 5 thing around the starting position. So the size here is 5, and it means that we have like 2 to get to the border. These are the equivalent, like 5 and 2 will be the equivalent of 131 and 65 for the actual input, but in this reduced example. So and the number that we're asked to compute is like a multiple of 131 plus 65. So this would be a multiple of 5 plus 2, for example 7. And if we go to 7, like 7 would be 1, 2, 3, 4, 5, 6, 7. We will get to the border of the second super tile in this way, but we cannot cover all the second super tile. So we will have like a kind of like a tip here. Maybe we could mark these things like 7 of this, and 1, 2, 3, 4, 5, 6, 7 here. 1, 2, 3, 4, 5, 6, 7. Yeah. Okay, and 1, 2, 1, 2. No, this is 3, 4, 5, 6, 7 in here. Sure, and then in here too. And then we would also get diagonally to every place. So this could be 1, 2, and 3. You could get. So you also have like the diagonals here, like covered. We can imagine those. I don't feel like drawing everything, but you could have like a diagonal that cuts here. So like it's okay. Like the second, let's actually write a little bit of the diagonal because I want to see something. So this diagonal would go like this and like this and like 1, 2, 3, 4. So let's count actually if I'm doing this right. So to move up to there, you would do 1, 2, 3, 4, 5, 6, 7. Yes, so you can reach this. And then over here also, this you can also reach. Like the walls are kind of very easy to avoid, at least in this example. I don't know if in the actual example they are the same, but you have this diagonal, and this is the same on every other side. But let's not care about that. So the second tile, the second super tile, let's actually kind of get that highlighted somehow. it goes up to here, right? So this is the second supertile, and you would have like this tip thing, which is similar to the second supertile here on the top and to the left and to the bottom. But it's interesting that the first supertile is also is all covered. The one over here is partially covered. It has like three. Yeah, it has like a 3 parts covered, and that's interesting. I wonder. I want to go up to 12 instead of 7 to see how actually things look. So let's do that. Let's bite the bullets and do it. So we add 5 on each side, and well, we will also get the diagonals. I don't know if I want to really draw the diagonals. Maybe I can do it without thinking too much about this, without thinking how stupid it is what I'm doing. Just want to visualize this, and of course I realized that I could automate this. I could do this with the code that we have already written and blah blah blah. I could also probably use some better text editing. Oh, I did a caps lock there. But anyway, we can reach. This actually kind of looks like a Christmas tree. So okay, this is just a more complex thing. So we will still have like a tip now, like the tip that we are seeing here in this supertile should be the same. Yeah, it is the same shape that we saw before, right? The second supertile is also covered. Now, one interesting thing is that the covering that happens on the second supertile is gonna be different than the covering that happens on the first, even though they look the same here because I'm covering everything with hose. In the actual puzzle, you only cover, like you have some parity, so you have like a checkerboard pattern thing with steps, which I think complicates things. Like this tile will be covered the same as not this one, but the one above if everything is covered. So there is some extra complications there, but let's not think about that too much. This is completely covered. The one on the top should also be, if I can, it would be this. It will also be completely, now up to here, it will be completely covered. Unless what I want to look at is the supertile here. This is interesting. So we have some, like some of, I wanted to see like the tiles on supertiles on the diagonal. So we have some of them, like this one, that have like a corner of them covered, but we have others that have kind of the other way around and a little corner uncovered, which is great. And I think these two cases are going to repeat because up here we have the same case as here, right? The top left, the bottom left corner covered like this. So okay. I want to count the supertiles. It's gonna be like not so easy, but I wonder if is we know that the number that we want to do is a huge number, that it's a multiple of 131 plus 65. Can we do just 65 plus, like, can we do this with the input, multiply like 5-fold or 25-fold, I guess in this case, like 2 to each side. So that would be 65 plus twice 131, so 65 plus 262. Do the actual like calculation of how many steps you reach, like kind of what we did on part 1, and then have like we will have a sample of all the possible super tiles I think that we would cover. I think we will have example like the tips. We know how the right tip would look, the left tip, the top tip, and the bottom tip in this 5x5 thing. We would know all the interior super tiles, how they should look, and all the different diagonals. Because I'm writing, like I'm drawing this here like a straight line, but what happens in the actual input is not a straight line. That is a simplification, because we have like there is these walls that you know you cannot pass, and some of these walls sort of form a barrier that you cannot pass. So maybe I could draw this, you know, and verify it, but I would assume that if we walk up to 65, the line that would get drawn here would not be a straight diagonal line. That is my assumption, because we do have some interesting walls here. Kind of my assumption. Maybe that's not true. Maybe that's not true, and I should test my assumption, because if that's not true, maybe things get simplified further. Right? Could be. Can we print that in like part 1? Look at the code, is quite little. Maybe we can print this. Because we have the reachable tiles. Yes, let's kind of do that. The reachable tiles, it's yeah. We can collect this. Okay, let's actually do that. I'm curious now. What did I change here? Yeah, I'm changing that to be able to. I modified the part 1 to be able to like extend this infinitely. Like that's why I'm using here reminder, like Euclid reminder and stuff like that, which is great. Isn't there like a, if you have an unsigned integer, can you have Euclid reminder but like unsigned? No, Euclid. There's a bunch of different div Euclid. What is? Oh, this is just the division. Okay. Oh yeah, but what I was wondering is like if we have some Euclid reminder that would get, like for unsigned numbers, we could pass like a signed divisor, or no, that doesn't make any sense. Forget about that. Yeah, forget about that. Yeah. Yeah, we need to like use negative positions here. Like that's something that we need to do. What I wanted to do was to draw some things. Like it's my suspicion that it won't be a straight line, but maybe it is. And if it is, maybe we can simplify this thing quite a lot. I'm not sure. I'm actually not sure if this would give me something that I need. But let's say simply reachable tiles. I'm going to collect this. Let's say in a hash set. Why not? And it's going to be reachable tiles, the iterator, we're gonna map these things. What do you have? The node is what I want, yes, and simply collect. That was easy. And now I want to walk the grids, kind of like what we are doing here. So I'm going to just copy this nested for loop. And actually, yeah, I also want the like the signed XY coordinates, so I really want this. And I'm going to just make strings. Let's line the string, yeah. I want this. Yeah, I think so. So if the tile, like let's paint like O's on the floor tiles that are reachable. So if the tile is a dot and reachable tiles contains this XY position, oops, then we are just going to yeah, oh, curly braces. We're gonna simply push an O, and otherwise, yeah, this could have been done with a map and collecting to the string, but anyway. Otherwise, we're just going to push the original tile, and then after this for, we're just going to print line this line. Okay. So we should have this, and I want to go up to 64 or 65. Let's say 65. I'm going to do this for the actual input. This wants reference. That should be it. Let's draw it in the bigger terminal. Cargo run. This step counter, yeah, inputs 21, input, yeah, go. Oh, it is a straight line. Look at that diamond. Oh, there's a little fella here that you cannot reach. You cannot reach this? What's... Oh, it's surrounded. Oh, that is... Haha. Interesting. Good edge case there. Ha. Look at me. You cannot reach me. Yeah. And you have another one here. Look at that. Look at my monkey brain detecting patterns. Yeah. Another one here. Yeah, this kind of things tell me that the corners of our diagonals are not going to be like, they are not, it's not like each corner adds the same amount of tiles than the other ones. But it's a straight line. It is a straight line. I don't know if this is actually useful, you know, but it's a nice thing to see. Look at that. Look at that rhombus. It's a sight to behold, I guess. That's a nice Gojira song. Sight to behold, indeed. Well, yeah, we know now that these diagonal lines, like, what this means is that the walls over here are not like what does this mean? The walls that we see like inside of this rhombus are not so connected that they mess up. Like they are not so big that they mess up the edges of it. Like you can get around those walls to always reach this diagonal. That may not be true if the starting point, the S, would be on the corner. So one simplification that I would like to do is to have like the starting position, like assume it is on the middle, but let's actually now, since our code is still thinking about part 1, we can test this with another starting position. You can run it like this and see, okay, we have a straight line there also, no sneaky tiles that you cannot reach. That's awesome. We can start it over here also, and we also have a straight line and no cheeky inaccessible tiles. Let's start with from all the corners and like just take a look around, like Limp Bizkit messing up your town. I don't know what it says, but yeah, here we have a couple of cheeky inaccessible tiles, and I'm now screwing something up with the input. Let's put the S over here, and that's the last corner, another inaccessible tile. But yeah, the diagonals are nice and flat, and I think that's probably a result of, well, of this map having like a rhombus here, kind of drawn like of empty of walls. So that's interesting. That's really interesting. Let's get the input back at where it originally was with the S in the middle. Okay, save. Yeah. So what does that tell us? I don't know. Because we also have like these cheeky bastards that cannot be accessed no matter the amount of steps we take, because they are enclosed by walls. And even if, like, you know, this is a perfect diamond and you do the like primality test, like evenness test to like exclude the checkerboard patterns, like we can actually do that pretty quickly here on the code. We can do this, basically filter the items that are not even in their cost, or yeah, only keep the even ones. So if we run now, we should see like this is actually the tiles, the O's that are, or sorry, the tiles that are accessible after 65 in this case. It is 64 in the part 1, but yeah, this should be it. And the cheeky one, let's search for it. Where is it actually? It's this one. No, let's see. It's kind of over here, like a little bit to the left. So it's kind of difficult to see because I'm looking for the walls, which are the hash signs, and I'm not finding it. So let's try to look for a pattern. It is where this kind of thing is. Yeah, let's look for this and this over here. So this and this is kind of over here. And I still cannot see it. It's difficult to see this with so many O's. Okay, let's draw a different character, like a little O maybe. It would be less less noisy. Yeah, okay, and now the walls are a bit more visible. So actually, can I see it? Let's not draw it. And like, where is the tile that gets not drawn? Actually, we can do this. Let's not move the mouse. Let's not filter this. We run it like this. Yeah, let's do this. I'll leave the mouse here. This is a very stupid way of doing it. I should be able to find it now. So I left the mouse in the same place. Now, where is the mouse cursor? Here. So this is not being reached, but also it wouldn't be reached by the primality, by the evenness test. Oh, but this is only on the first super tile. On the second super tile, we will have like the opposite numbers for the checkerboard. So this would screw us over. Like if we do just like a rhombus calculation area and I don't know, the checkerboard pattern, and like exclude the checkerboard pattern and exclude the walls, still like things that are enclosed like this would mess our calculations. So it's really nice that really nice and really like, you know, very nice edge case to include this on the actual input. So okay, this is not really, I don't think that this observation of the diagonals being straight, like I don't see how this helps us, but let's comment this or maybe throw it away. I don't know. Let's go back to what we have in part 1. What I was thinking with the example is to do this like 5x5 tiling of the inputs, and sort of then we would partition this, like we can partition this then on the resulting like super tiles that we have, and we will have examples, like count then the number of reachable tiles on each of those, and we will have like examples of everything that can appear, I think, in the final thing, the big one, and we should learn how to count those. And maybe what we could do is do a couple of these, like a couple of sizes, and see how those numbers change. And so we can sort of learn how to do like the arithmetic. I think that's something that we could actually do now without even doing this partition. We could, yeah, let's see how these numbers get bigger, right? That should be more or less easy. Let's extract. Let's get rid of this, because this drawing was, well, it was interesting, but it didn't give me what I wanted to see. We'll have the grid, sure. Let's extract everything else into a little function, and this should be like count reachable tiles. Yes. We're gonna receive this, which I'll just put in a type alias, our usual grid type alias, more font size. The result, let's use this. I don't know why this needs to be a result. Like, where are we? Oh, the starting position. Yeah, okay. Like, sure, why not? Not very pretty, but it's okay. I don't want to care about that. It's like, if we assume that the starting position is at the beginning, that would be easier, I think. But anyway, we can unwrap, so no problem with this. So what do we want to do? What we need to do is, where did I have the big number? I think I used Ruby. Yeah, a Ruby calculator, Ruby session. Yeah, Ruby REPL. That was the name that I was looking for. So this exploration is already taking me 40 minutes and I didn't do anything. Great. I wanted to see, this is the number that we want to check. And actually, you know what? One thing that we checked last time, I don't know why Control U is not deleting. But yeah, let's go back to the terminal actually. We saw that this thing was not a prime, but it's also like, it's also not far away from being prime. And actually 5 times 11, well, it's 55. Which I don't know, makes me think about 65, but maybe I'm seeing patterns where there isn't. Oh, look at this. This ends in 65. So subtracting 65 from this is very easy. This is a multiple of 131, like we know. Okay. Let's see how this number, so we have this, which is the answer to, well, we would need to parameterize this by this number, like reachable tiles, we'll say steps, and this cost is I32. What? I32 is not enough. Why are we assuming that? Count reachable tiles. I mean, well, it's in the millions. Yeah, it's not. Yeah, I32 is enough. Yeah, no real problem. But we can use. We can just use something that makes more sense, at least to me. This is the number of steps that max steps, I guess we could say. Or this is actually like the exact amount of steps. Let me think. Think. Yeah, let's say this is max steps. We're gonna compute this. Actually, I'll go back. Steps count. That's what we need to reach because it's like an exact number. And like the original, like the part 1 asks us to do 64 of this. 64, and we now want to explore different numbers, but they are not even. Like actually it's a multiple of 5 what we need. So this thing about getting the ones with even cost, it's not correct. Like it won't be correct for 65, and we can check this with the input that we are given. So this is not too bad. Let's call this thing for 64. This should be the answer to part 1. Let's actually run this with inputs. Why am I running this like this? Just want to run with cargo run. Input, no needs for release build, I think. This is the correct answer, right, for part 1? Yes, it is. Okay. So we are doing this fine for 64. Now, the sample I obliterated this. So let's actually copy this mess and put it on a new file. Sure. I will just call this thing, 21 sample, I don't know, notes. This is just for some notes. And let's go back to the actual sample that we care about, which is this. Because we have some answers here, and I want to see if those answers are correct. So I don't think they shouldn't be when we do this. Oh, but all the examples here, all the numbers are even, which is kind of not something that I like. Well, we don't have a number, like an example with a known number that will be non-even. But surely, like, one thing that we can do is, okay, for the sample and the number, let's say, let's check something. Let's pass 100, for example, and we run with the sample 6536. Is this correct? Yes, it is. Like, fine, perfect. But if we run with 101, this should give us a different answer. Will it? No, it gives us the same answer, and that is because we are doing this filter that will get rid of the tiles that you reach on 100. Since 101 is odd, we need to check for the tiles that have an odd cost. So let's say, evenness. It's gonna be steps count mod 2, and here we want to check that this thing, like the cost mod 2, is equal to the evenness that we are expecting. So if we run now with 101, we get 6684, a bigger number than before. Great. And if we run now with 100, it should be the same. Okay, so now I believe that this naive part 1 answer, and that we are going to reuse most likely, is working also for odd number of steps. Great. Now, what did I want to do? I wanted to let's leave this thing as 64 is the part 1 answer. I am going to leave it commented, but I'm going to also try some other things. Count reachable tiles for 65. Let's say that this is, like, I want to see how these things grow, adding, like, from 65 and then adding multiples of 131. So let's say, I don't know, count 0 is going to be this, then count 1 is going to be this, plus 131, plus 131 times 2 is going to be count 2, count 3, count 4, let's say. That should be enough to, if there is a pattern, I would like to see it. So let's print these guys. And you don't like this because you're a result, right? Yeah. Don't be. Do early returns. And you, the grids. Oh, you don't need now to be you were already a reference, but better not be a reference and pass by reference more explicitly. If you run this, well, the example is like, I don't care about these numbers, right? Does it run? Oh, it takes it takes some time, but we get numbers. These are numbers that I don't care about. So let's run for the input and let's run in release mode. And we have numbers. We have numbers indeed. Look at how these numbers increase. It's almost like tenfold from 0 to 1, then 2 is like 3 times more. This is like 3 times, no, twice more. Let's see how the difference, like the differences of this are. So if we do, I'm only going to have the differences for like, well, C1 minus C0. And here I'm going to do this. Like, how much is the difference with the previous result? Because, well, they are not incrementing linearly, that's for sure. But are they incrementing like quadratically? That would be awesome. Oh, wait, look at that. Yeah, this number looks like double this, right? And ooh, look at that. Actually, we can do the differences of differences, and this reminds me of the other puzzle that we had like this extrapolations of differences. I'm doing something similar here, but like manually and ad hoc. But here we would need I would need to have the differences. How do I do that? This in a like I want this number minus this number. So let's actually do something like and let's the difference be all this and we can, do we have the, I don't know what happened with my multi-cursor there, but I think I can still paste. Yes, we have the differences, and let's now do d2 minus d1. So this is the differences of difference, kind of like the second derivative, I think, if like in a non-contiguous fashion. I don't know, my math brain is very rusty. No pun intended. So if we print this, are the differences? Yes, they are. Look at that. Look at that. They are the same number. So maybe we don't need to do any of like this idea that I had of doing the 5x5 super tile thing and then extracting all the super tiles and adding them up. I could extrapolate this thing, like this sequence. If these things continue, and I have no reason to believe that they won't, because we are now just adding 131 each time, and the differences of the differences remain constant, then this is a quadratic. Yeah, this is a quadratic thing. That's awesome. That's awesome. And I should be able to, like, how do I extrapolate this? we could linearly do like a because the number of doing like this divided by, like, this is the amount of steps that we need, we divide it by 131, is like 200,000. So we can do that linearly, like do 200,000 calculations. They will take no time. Like we continue. Well, we don't do this, of course. What we do is kind of similar what we did in I don't remember which extrapolates day 9 it was, where we have these sequences and we were doing like extrapolations back and forth. Oh, this thing was this puzzle was amazing. But we can do something similar here. These extrapolations are kind of like the second derivative, if I'm thinking of this correctly. So we assume that this remains constant, these differences remains constant, and we keep adding then to the first derivative, like these differences, we increase these by these numbers, and then we add this by the differences. So we need to like compute the d1s, d2s, and d up to where we want, and then add this. Start with c0 and start adding things together. I think that would work. That should work. What is like the arithmetic expression of that? Right? Because this starts to work even with from c0. I think. Where did I have? Oh, here. So c0 means the amount of reachable tiles at 65 steps. Like the difference between C0 and C1 is this. And then the difference between this difference and the next one is already like the constant that we want. So it's not like the first thing starts at 65 and plus 131 or plus twice 131. No, it already starts at 65, like to do this quadratic growth. So this number, however, like the first difference that we see is not this number. That's interesting. It's close to, but not quite. Actually, no, it's not the difference. It's 110. Yeah, it's kind of a similar difference, but it's not just this plus this squared or something like that. Well, no squared, times like n squared. So what I'm sort of thinking is, this was really interesting. If we think about sort of this function where instead of this would be this times 1, right? And this is the same. Yeah, this is let's write it all the way times 0. So this is just a function of this number, this n thing. And I think we have seen that this thing is quadratic, right? We can write it down. Let's say let's start to use like mathematical nomenclature. F is going to be this thing, and I don't care about errors, just do unwrap here. Don't think about error. This times n. My idea is that this is quadratic. How do we extrapolate to where we so these things would be like f of whatever, f of this basically, without question mark. Beautiful. Why you don't? What's your problem here? Type it mismatch. U64. Who is... So you must be U64. Don't be something else. Yeah, don't. If we run this again, we still get the same... Yes, I didn't make a stupid mistake. Okay, so what I want is to have like the formula of the quadratic thing. So let's like what we are supposing here is that f of x, we can even be extra mathematical and call this thing call this thing x, like mathematicians. If this is a quadratic, this would be a times x squared, and I can, look at that square symbol there. Probably not very visible. And let's write it like this. Squared. Actually, I kind of like this. Yeah, let's do it like that. Plus b times x plus c. And I would like to, like, if I can know a, b, and c from here, and if this is true, that this is a quadratic, which I think it is, for what, because like let's think, I'm saying something that is not very obvious, but if you consider like a normal quadratic, like let's say x squared, like that should be the easiest one, right? And how does x squared go? Well, it goes something like x to the 0 is 1, then x to the x squared. Sorry, 1 squared is 1, 2 squared is 4, then it comes 9, then it comes 16 and 25 and so on. Now the difference between this and the previous is gonna be 3 in this case, then 9 minus 4 is 5, then 16 minus 9 is 7, then 25 minus 16 is 9. And you can see that these things, well, the difference are not the same, but they are increasing linearly. 3, 5, 7, 9. And if you do then the difference of the difference, like 5 minus 3 is 2, 7 minus 5 is 2, 9 minus 7 is 2. So that is kind of the same thing that we saw here. The same freaking thing. And in this case, well, a would be 0, and c and b, a would be a 1, and b and c would be 0. If you have a different c, it's like you start from a different number, kind of, but then you add, like the quadratic progression is still kind of the same. So how do we now know a, b, and c? Let's put our mathematical hats on. So c is the easiest one, because c is basically f of 0, right? If we do f of 0 here, we multiply this by 0 and by 0, so let's say what I want to do now is find coefficients a, b, and c. a, b, c. C, I think, is f of 0. So we can write that right away and say, let's see. Actually, it is what c is 0 here. What we have for that, right? Yeah. Yeah. Now to compute a and b. How do we do that? Well, for a, I think a is kind of what we see with these, like the difference. I think I'm going to like need a couple of these. Well, we can extract that later, but the difference of the differences, I think, is kind of like c, or maybe twice or half c, because that's basically kind of like the second derivative. Like if you think the first derivative, f derived, the first derivative would be 2ax plus b. And the second derivative then is 2a. And I think this then is 2a, if I'm not mistaken. Probably I'm mistaken, I'm not sure, but let's say f double derived of x is 2a. So yeah, kind of. So it will be these, which the names here are a bit messed up. So I think I want up to f2, let's say. Okay, let's copy this. I want to call these things f0, f of 1, and f of 2. So yeah, sure, you will be f of 0. Now u, then I'm not sure if this is correct, but I will say a is then this d2 minus d1, which d2 is f of 2 minus, yeah, let's say questionable, but it's not like the derivatives, but let's see if this sort of makes sense. Like I want to, yeah, I want to have the coefficients. What did I say? d2 minus d1. So d2 is f of 2 minus f of 1. So f of 2 minus f of 1. All of this minus d1, which is f of 1. So f of 1 minus f of 0. All of these divided by 2, I think. It's like, not really sure, but let's see. I can probably do some, like, not use derivatives and do algebraic things for like getting a and b. Yeah, because we can say then here, if this comes from f of 0 being a times 0 plus b times 0 plus c. So then cf is f0, right? That's kind of the thing. Well, let's express this here and see. Like I'm not sure if this is going to be correct, but if we have a, then getting b should be pretty easy with with a and c already. And if we I'm pretty sure about the c. I'm not very sure about the a. But if we mess this up, we should know. Minus f of 0, and actually I would like to know if this number, like this number, well, yeah, they are even here, so divided by 2 we won't be losing anything, but I don't know if this is exactly correct, but let's roll with it. Let's roll with this. And then if we know all of this, how do we get b? So b is gonna be we can evaluate f of 1, and for f of 1 we'll have a plus b plus c, because x is 1. So then b is a plus c minus f of 1, I think. Yeah, that makes sense. I mean, f of 1, this. So let's say let b equal a plus c, yeah, minus f of 1. And the one thing that I'm doing wrong here is I'm subtracting things, and this could underflow. Let's run this in debug mode to check for math underflows. We should have A, B, and C here. So let's print A equals A, B equals B, and C equals what? C. All right, and then what I want to do, if this was correct, let's have a new function. Let f2 be, we're gonna do sort of the same. We're gonna take an x of u64, but we are just going to do this. No, this. This is gonna be a times x squared, which is just x times x, plus b times x, plus c, right? And what's your problem? What? A is U size? Because these things are returning U size. Great. These are costs. Why is the cost? No, it's not cost. It's because of this count. Just do this. Just do this and return a little U64. Why not? So now they shouldn't complain. And now we should see if f2 gives us the same as f1, as our original thing. So let's I was going to say assert, but I just want to see the true false printing. So we want to see if f0, what we calculated with first, is the same as f2 of 0. That should be easy enough, but also f1 and f2 should be the same as this, and one that we didn't use, f3, is it the same? And we previously calculated up to f4. Let's do f to f3 because I want to run this in debug mode to check for underflows. Run. Falses, and falses. But the first one was true. That was promising. How false are these things? Like, how wrong are we doing this? Let's print like this. Let's print two numbers. First one is true. The second one is already, I'm doing it pretty wrong. But the second one, we got close to actually the second one from here, and then it goes off the rails. So we did something wrong. Oh, A, B, and C. A is, okay, C looks correct because that was the easiest one. Now A and B are equal. That is, that's not good. How did we get? Oh yeah, because I did it wrong, right? B, like we know that. Oh, look at that! I said f of 1, and then I use what? F of 0. Let's use f of 1, maybe. Was this the mistake? Not quite, but not so, like, it's less wrong. Now it's a bit less wrong. Okay, so we are getting like quadratic, probably like this function that we are doing here, f2, is also a quadratic. Like they are not the same, clearly, they don't give the same results. But how does f2 grow? So I want to print that maybe. Let's print f2, then f2 of 1 minus f2 of 0. These are like the differences, so let's actually kind of d2, d3, d4, let's have them here. Kind of the same thing that we were, I could reuse this, right? But I don't know. This is the d3, d4. So the differences, and then I want the differences of the differences for this last one. So we want d3 minus d2, and here on the last one we want d4 minus d3, right? So we're sort of doing the same. What's your problem? Your problem is that you don't have enough printing, sure, and you have more printing than necessary. Okay, how about this? About the second, what? Oh, I'm being an idiot. So the differences, d2 is actually not d2, but well, is this. Then the other one is 2, 2 and 3. Whoops, where did I jump? I don't know. 2 and 3. This is minus this. Okay. Yeah, these names are a bit fucky, but that's fine. Let's run. Okay, so we did this wrong. Like the computation of the differences, and it should have been 30. The differences of the difference. So surely, like this is the coefficient for the quadratic term. Yeah, this thing about the double derivative, I'm not really sure about that. We are running none of this in debug mode, right? Yeah. So if any of this subtraction would have given us a negative number, we would know, but they didn't. And we know that a is kind of a big number. That's kind of a big number, and it's making this thing grow much faster, like 21,000 when it should have been this. The difference of the difference. So let's actually do some better algebra. We have f of 1, f of 0. So actually, let's write the expansions for, like this is trivial. Let's write also f of 1, we have it written here. I want to have this, guys, and do some algebra with this, because I'm pretty sure that with these three, f0, 1, and 2, we should be able to get what we want. So this should be a times 2 squared, so basically 4a plus b times x, so this is 2b plus c, right? A is messed up. Let's not think about the... I think this for b is actually correct, because this comes from this, right? Yeah, b is... Oh, I did it. No, sorry, I did b wrong. I did B wrong. I don't know if A is the problem. I did B wrong. B should be F1 minus A minus C, and I did it the other way around. Shit. F1 minus A minus C, and this could underflow. And if it does, I'm sorry. We'll need to use signed integers. And I think this will underflow, right? If we do this, yes, it did. We underflowed. So how do we fix this? Let's make all of these things be. So we know that this is positive, sure, but let's use 64 bits signed numbers, and here also take one of these, and did that little thing change everything to, yeah, these are all now signed, sure. B could be negative, why not? Let's run now, and okay, B is negative. The increase is still, this is still wrong. And I actually wanted to, here we have F2. Let's also have a column for our original thing, the original function. So F0 here, F1, F2. So F1, F2, I just want to see, and this is F of 3. F of 3 is taking some time to compute, but oh, look at that. F1 is now correct. F now is now correct. What does that mean? What does that mean? I mean, yeah, I mean F1, like our F2 of 1, like this linear approximation is now correct. It now coincides with the actual count when n is 1. So I think that is mostly due to B, because F1 is like this, and C is not growing quadratically yet. So yeah, I think that this C, no, sorry, C, no, the A coefficient is messed up. It's the differences of the differences. So that made me think about the second derivative, but it's probably not. It's probably not that. But B is now correct, so we are approximating this correctly. But B comes from our calculation of C and the F1, so it sort of makes sense for this to be correct. But A, from our B comes from A and C. C, we know that it should be correct. A, I think it is the problem. So how do we compute A? I think we can compute it doing something with these two, right? Yes, we can do F2 minus twice F1, and we get rid of B's, I think. So let's say what I just said, F2 minus twice F1 is equal to F2 is, well, we're gonna have 4A minus 2A, right? F2 minus twice F1, yeah, 4A minus 2A should be 2A. Then 2B minus 2B, because it's 2F1, cancels out, and C minus 2C is minus C. I don't know if I did that correctly. And now we can solve for a. A should be f2 minus 2 times f1, all of this plus c, and all of that divided by 2, if I'm not mistaken. Divided by 2. So let's write that down. Is f2 minus twice f1, so kind of similar to what we have, but not quite. 2 times f1 plus c, all of this divided by 2, and I don't know if this division by 2 is correct. Maybe I want to print this. Let's print line. 2a is this. Okay. And what happens now? 2a is an even number. Oh, 2a was the number that we were seeing before. So it was just this number divided by 2. The differences of the differences divided by 2. How did I mess it up so bad? Like if this is the double, what did I do? Don't understand. This is the difference. The differences of the differences that we were seeing before. Like I feel like the previous calculation that we were doing should have been right. But okay. Oh, now look at that. Now it coincides. I was I was worried about this, but now our f2 coincides up to n equals x equals 2, but also x equals 3. Look at that. So I think we got it. But then this makes a lot of sense to me. Like we did some algebra between these two, didn't think about derivatives or anything, but like the derivative thing was not wrong, I think. What happened? Like this should have been 2a, and so then a should have been equal to the differences of the differences. So f2 minus f1, all of this minus f1 minus f0, and I just want to do this again because I feel like this is 2a, so all of this divided by 2 should have been our answer. So let's call this thing a prime or a2. Kind of confusing the 2 over there, but like it's another calculation for a, like another opportunity. I just want to see like why are they, because these should be 2a. It's actually f0. Let's actually print this. Print line to a prime. It's gonna be this thing. Aren't these two things equal? Remove parentheses here. Yeah, they are. Like, what the hell did I just messed something. I messed something stupid before. If we do this, then it's the same a that we should be computing, right? Yeah, this a prime is the same as this. What did I do wrong? Like f2 minus f1 minus f1 minus f0, all of this divided by 2. Like, sorry, I just have this itch now. I want to see what I was doing before doing this algebra thing, blah, blah, blah. this f2. Oh, look at this, I'm an idiot. I didn't divide by 2 the whole thing. Oh, it was a stupid mistake. This whole thing should have been divided by 2. Ah, damn. Okay, let's redo everything until what we have. Man, what an idiot. I got the reasoning right, but I just wrote the code wrong. So these are 2 different ways of computing A. One is doing this, and one is doing this. Both are fine. Both gives us the same idea. This one depends on C. This one does not depend on C. What do I prefer better? Probably this one. Like the first one is sort of easier to explain. We are not talking about derivatives or anything, so that's fine. And then B is just a simple thing over there. Yeah. F of 2 is okay, yeah. It's the reasoning for A. Great. So what do we need to do now? I just got relaxed and thought, okay, I think I have it, but I don't know if I have it. We need to compute this for the large number that we are asked to do, which is this number of steps. So if we do this minus 65 divided by 131, and call, well, we could call our original f with that number, but that will do the actual count of all the things. What we want to do is call our approximation now. That is just a quadratic. Let's call this thing, this is f extrapolated. And let's now call f extrapolated with this number minus 65, all of this. I said 65 and I wrote something different. All of these divided, it's gonna be integer division. Actually, like, we don't need to subtract this because it won't do any difference. Integer division, and yeah, let's just print this. Let's just print this thing. This, I think, should be the answer for part 2. And we got a number, a big number. Is this the answer for part 2? Yes! Yes! It was! Awesome! Maths to the rescue once again. Maths saved the day. Awesome. That was great. That was great. Okay. So I think that was it. That was what I wanted to do. It was actually 1 hour and 30, but we got the answer. I'm so glad about this. I don't know how to explain this answer, but it is an answer. Like, what is even happening here? I don't know. But it is an answer. Okay. What can we do to like commit this as an answer to? I mean, I can just commit it, of course, but let's actually say f quadratic, I don't know, extrapolated quadratic. Quadratic is not written like this. I think it is like this, yes. Beautiful, beautiful thing. This is just crazy. Crazy thing. We can have that. Count reachable. Like, I don't like this unwrap, of course, but I mean, we can just maybe to get rid of this unwrap, we could do this and say as U60 I64 here. But man, this was so interesting. I just want to yank this from here and put it on our answers. Can put this there. Now checking all, like, the answer for parts for the sample won't make any sense, because this was all thought for our actual input and not for the sample input. And I don't care about the sample, to be honest. Like, I don't really care at all. I just want to, like, express this in actually this thing that I changed right now. I don't like it. Let's go back to this and keep it like sweet and short. Short and sweet over here. We can make this thing like return some, like, propagate the error. Like, will it can we make it this thing to return AOC result of something? And probably need to do an OK of this. Almost there. Okay, this kind of works. It's ugly, but it works. And then we can, like, propagate. Yeah, and we got error propagation back. This thing should still run and give us the same answer. Yes, it does. Great. And this is basically answered for part 2. So let's call this thing, let's answer 2 is f quadratic with this. And we're gonna leave the answer for part 1 here and just print answer 1 and answer 2 to have a complete solution. This probably requires some comments about what we're doing here. This code is all right. One thing that I would remove from here is this find start position thing. What I would do is to assume that the S is on the middle of this thing. So let's do this. Let's say that start position is just size divided by 2 and size divided by 2, and then just check if grid at what is this start position? Start X and start Y, I guess we could say, and just pass this guy to Dijkstra like this. We're not using start position for anything else, so this should work. This, however, the positions of things. Yeah, there are some things that the function that we just removed. Let's go back a little bit. Return positions, yeah, of signed integers. So we're gonna fix this. But let's say grid at start y and grid at start x. This thing should be the start position. Like, we are just going to assume this. So let's say if this thing is not the starting position, then we error out. Let's say expected to start in the middle of the grid. And we just bail out of this, and I think these problems can be fixed by taking the size as a sized integer here. And we can actually work with 64-bit numbers just right away. We have start x and start. We'll convert this to usize only when accessing, but otherwise they will still be signed. So here what's your problem? This, because I'm converting to I size when it shouldn't be needed. Yeah, okay, that's better. Do we have the same results? Yes, we have the result for both parts. That's great. Yes. So I'm just going to leave a little comment here. For part 2, we do a quadratic extrapolation of this function and this should have an explanation of what are the assumptions that we are making, like to do explain why we are assuming that this is quadratic. So one thing is like, okay, we know that this is quadratic, we have already checked it, we know that we get the right answer, but we can also like leave like some assertions here, like we know that we should know that we got this right. So let's assert EQ, or actually if it's about inputs, it's not going to be quadratic. So well, yes, let's assert. Let me write what I want to write. So let's assert that f0 is the same as f quadratic of 0, right? And we're gonna do the same for f1, f2, and now and I guess we can also do like an extrapolation of, although we know that f3 is taking some time, so let's actually time this thing. Time, yes, step counter, blah blah, but not for the sample. Let's run this for the input. How long are we taking to run this thing? It's already taking some time, the release in release mode. So I don't know if I want to do like a check for f of 3 if still is extrapolating correctly. Oops. This. I mean, it is passing the check, but it's also like increasing our runtime significantly. So yeah, this can be assertions here because we did the quadratic approximation based on this number. So it would be a bug if this didn't work, I think. I'm not really sure about any of this, but I think if you take 3 points like this, you can always find a quadratic approximation, and that's what we are doing here. And then we are assuming that it goes on. So yeah, if it's not the case, like if the input is doesn't comply with the assumptions that we had, then like if it doesn't meet the assumptions that we have done, then it won't give a good answer, this quadratic approximation, a correct answer. But that's, I mean, this is not something that works for any input. It works for the inputs that we received. So, but it won't crash. That's my point. We're just going to run the part 1 thing a couple of times, and yeah, and be fine with this. I would like to like maybe not hard code this. Explain to do the hard code 131 and 65. Yeah, kind of. Yeah, because 131 is just the length, the size, and 65 is half the size. We can do that. Okay, I think that will be it for this video. I'm glad that we got some answer using actual like math or math looking things, and we didn't have to do the like this thing that I was thinking about doing. We're actually running this when we run f of 2 is exactly this thing that we are running, but we are not like then stitching and the super tiles and then like multiplying things together. Like all of that is taken care of because this is quadratic, so it's the same thing. It's the same result that we would have gotten from doing this approach. But this is much simpler, I think. So yeah, I'm glad that this worked. So that will be the end of this video. And well, as always, if you have been, thanks for watching, and see you later. Bye bye. Bye.